My name is Wolfgang Utschick. I'm professor at TUM and I'm heading a research group in signal processing for wireless communications. Our most research activities are on concepts for what we call the air interface in wireless communications. This basically means that our research is on signals and how they must be designed such that they travel most efficiently from the transmitter to the receiver unit in a mobile of a cellular infrastructure to our smartphones and tablet PCs in our hands. In particular, our group concentrates on a special feature of the air interface, namely MIMO. MIMO stands for multiple input, multiple output, which here refers to the deployment of multiple antenna elements at the transmitters and receivers of communication links. MIMO enhances the wireless communication link with an extra dimension in space. This means that the advantages that come with MIMO are very similar to the benefit that we have with 2 ears instead of only 1 ear, which allows us to distinguish sounds from different directions. For the technological equivalent, the MIMO system, so to say, this means that the technique allows to exploit directivity of signals for an extra dimension or a resource in top of bandwidths for the wireless communication link. This is the reason why MIMO has become an enabling technology for the current 4th generation of mobile communication, better known under the name of LTE and LTE Advanced. For future generations of mobile communication systems, the next one is the 5th generation, we are still seeking solutions for keeping pace with the ever-increasing demand for higher and higher data rates in a more and more connected world of already today and even more tomorrow. One of the most promising solutions for these challenges is massive MIMO, which is MIMO, but with a massive number of antennas, hundreds to thousands, at the transmitters. Obviously, this will change the shape of future antennas dramatically. You might imagine that the whole facade of a building becomes a huge antenna array with multiple of adaptive integrated antennas. Massive MIMO is definitely not just a scaling up of standard MIMO. On the contrary, in order to obtain the potentials and benefits from massive MIMO, we have to reinvent and to rethink lots of concepts and algorithms from standard MIMO. And that poses a variety of very interesting and challenging research questions for us researchers in academia as well as in industry. Some of these challenging questions you will get introduced to in today's session.
And now
this session is about massive MIMO, which is one of the most promising solutions for the 5th generation of mobile communication networks. And this is our today's agenda. I will first talk about the wireless communication link, which suffers mainly from the attenuation of the signal strengths and the interference between users. Then I talk about multiple antenna systems, referred to as MIMO, which are a well-known solution against these problems. And then you will learn about massive MIMO, which is a promising candidate and has additional advantages over standard solutions. Let's first start with the physical wireless communication link, the so-called SISO link. SISO stands for single input and single output. And this situation is illustrated here in this graph. Here we have one single antenna element at the transmitter, which is radiating electromagnetic wave fronts to the receiver on the right-hand side. The main issue with the wireless medium is the attenuation of the signal strength. So if the signal has to travel a couple of 100 meters or even kilometers from the transmitter to the receiver, the signal experiences a huge attenuation. This is about a factor of 100 million, which refers to an attenuation of 80 dB. That means that the signal at the receiver is very, very weak. One of the solutions to this problem is the deployment of multiple antennas at the transmitter, which is MISO, multiple input, single output. In order to study this in more details, we will replace this more abstract illustration by the following notation. Here, each antenna at the transmitter is linked to the antenna at the receiver and characterized by a complex number H1, H2, H3 and H4, which relates to a so-called baseband representation model. This also allows that we are able to describe the signal at the receiver, the signal Y, as a linear combination of the transmitted signals X1, 2, 3 and 4 at the transmitter, which arrives at the receiver with linear weights H1, 2, 3 and 4, which equals the respective channel coefficient. This can also be expressed in a more compact version by an inner product of the channel vector H with the transmit vector X. And in all these models, we have, of course, an additional noise term that refers to any kind of temporal or other kind of noise at the receivers. The question is how to design this transmit signal X1, X2, 3 and 4. If we want to transmit a dedicated signal S to the receiver on the right hand side here. And this is done by one of the most prominent solutions here in our solution, by the so-called matched filter. The matched filter means that the coefficients, so the weight factors W1, 2, 3 and 4 of the weight vector are equal to the conjugate complex entries of the channel coefficient, or the channel coefficients. This is here. And this has the effect that we are able to concentrate or to focus the radiated waveforms in the direction of the receiver. And this means that there is no energy wasted and no power wasted into direction where no receiver is. The respective received signal then, Y, is equal to an inner product of the channel vector H with its conjugate complex copy normalized by its strength, so the length of the vector. So this basically means that the received signal is the dedicated signal S with a scaled version with a factor H which is equal to the length of the channel vector, the norm of the channel vector. And then of course we have the respective noise. So let's summarize. If we choose the beamforming vector as a matched filter, so the W is equal to the conjugate complex of the channel vector, normalized by the length of the channel vector, we have this received signal model. The received signal Y at the receiver is a scaled version of the dedicated signal S, where the scaling factor is the norm of the channel vector and some noise. For the relation of the signal portions, so the S and R, which is the ratio between the power of the desired signal over the power of the noise, is this term. And this shows that under certain requirements and assumptions, this is proportional to M, which is the number of transmit antenna elements. It is called the array gain. Okay, this brings us to the next step of this session, and this is multi-user communication. Because communication in a cellular network is not a single show between one base station and one user, because all of us want to have communication services by the providers. So in order to cope with the huge demands of communications in a network, it has been found that it is useful to have multiple receivers served in the same bandwidth and during the same time slot. And what this means And what the problem is with this is, can already seen here with this illustration, because each receiver not only gets the waveforms which are dedicated to him, but also will overhear the signals which are actually meant for the other users. And this phenomena is called interference, and is the second major problem in wireless communications. In order to study this in more detail, we again replace this illustration by a more mathematical notation. So each link from the base station to receivers is represented here by a channel vector. We have channel vectors H1, H2, H3 for the receivers 1, 2, and 3. And each channel vector consists of so many channel coefficients as we have transmit antennas, 1, 2, and so on, n. For the signal model, that means that, for example, at receiver I, so let's think this is the ith receiver, that at the receiver I, the channel yi is the inner product of the respective channel vector hi with the compound signal vector x, plus a noise term, the individual noise term at this receiver I. So, but what is the compound channel vector x? This is the linear combination of all dedicated signals to all users, because we have a shared medium. All users share the same bandwidth and the same time slot. So the compound signal is the linear combination of all signals with their respective beamformer, which is a matched filter in our case. So let's summarize. The signal now at the receiver, if we plug in x in the transmission model, consists of these three terms. There's first the first one that we have already been introduced to in the single user model. This is the dedicated signal to user I times its norm of its channel vector. And then we have the noise term. These have been the terms that we already know from the single user case. But now we have these signals which come by the overhearing of the other users. And these are these ones. And you see here, this term depends on the inner product of the channel vector of the user I with the channel vectors of all the other users. So if this term does not vanish, which is typically the case, does it not vanishes, then the interference in the worst case might even be larger than the useful signal. And this obviously will corrupt the signal transmission, the information transmission, and even maybe it comes at breakdown of the communication link. So in terms of signal to noise or signal to interference and noise, this means that we have here an enhanced version of the signal noise ratio, the so-called signal to interference and noise ratio. That means that in the denominator here, we have now an extra term, which comes from the interference. And this is a major problem in multi-user communications. And one of the typical solutions is either equalization at the receivers or pre-equalization at the transmitters, which means that we would not only choose a simple version of a matched filter, but we would use a pre-coding or pre-equalization at the transmitters that take into account this phenomena. But that's a very complicated thing. And there is another solution. And this is the topic of today. This is massive MIMO. So first of all, what's massive MIMO? It's MIMO. Multiple input, multiple output. So multiple antennas at the transmitter and multiple antennas at the receiver side. But in this case here, the number of antennas is huge. We talk about hundreds to thousands at the transmitter. What does this mean? First of all, we get the typical advantage from multi-user elements at the transmitter, and that is the array gain. Because we learned that the SNR is proportional, under certain requirements, proportional to the number of antenna elements. So if we have a huge number of antenna elements, we have a very large SNR. That's good news. But we have more. Because massive MIMO allows what we call asymptotic orthogonality. Under certain requirements, it happens that the inner product of two different channel vectors become zero. What this means, let me explain 2 slides ago. That is here. Because here we see this is the major term that accounts for the interference. And we just learned now that in massive MIMO, this term tends to 0. And that means that the SNR again becomes an SNR. We get rid of the interference. And that means also we just employed or deployed simple matched filter solution for the beamformers, not taking into account the interference situation. We get rid of the interference. Means we can afford robust and simple signal processing methods, which is the matched filter solution. Yeah, this has been a first introduction into the first steps of massive MIMO. And now comes the task of the week. To this end, let me explain you another thing, and this is, where do we know the channel information at the transmitter? Because I just explained you that a very appropriate solution is to take the matched filter solution. That means that the weight factors at the transmitter are equal to the conjugate complex values of the channel coefficients. But where does the transmitter know these channel coefficients? And here the uplink training has been proposed as a solution for massive MIMO. That means before the transmitter can send information to the receiver sends information in. Prior to that, the receiver transmits information to the base station. But it transmits symbols which are known on both sides, so-called training symbols or pilot symbols. Based on these known properties of these symbols, the transmitter can estimate the unknown channel vector h. Of course, there will be some noise which basically leads to a corrupted version of the right channel vector. But that's okay. But the problem is something else. The problem is that at the same time, there might be a second user which also wants to have access and also wants to get the service from the base station. And it also sends training data to the base station. So if the base station, the transmitter, is not aware about this, it might happen that it considers this part of the signal as part of the original user here. And that will have dramatic effects on the downlink when the base station is transmitting data to this user. And this effect is called pilot contamination, because the part here, the interfering part of the channel vector, contaminates the channel information of the other user. And here come the questions for you. You have seen pilot contamination. And what I want to know now is, what is the impact of pilot contamination on the downlink communication mode? And the second question is, what kind of countermeasures could be thought of? And I give you a hint. In order to understand the effect of pilot contamination in massive MIMO, compute the SNR, but taking into account pilot contamination. So go to the formulas of the SNR and consider pilot contamination, and you will get the answer. Thank you very much.